Welcome to the tutorial from HPO to NAS, Automated Deep Learning at CVPR 2020. I'm Cedric Archambeau. I'm at Amazon Web Services. I'm based in Berlin. And in the first session, I will talk about automated hyperparameter and architecture tuning. So we've seen in recent years the successful application of machine learning and deep learning in practice. For example, computer vision is used in autonomous driving, speech recognition in virtual assistants, and we've seen the application of computer vision in cashierless grocery stores, and of course, machine learning and deep learning have been used for quite some time to search and recommendation. We've also seen the successful application of deep learning in games, where Lee Sedol, one of the best players of Go, was beaten by AlphaGo, to his surprise and to the surprise of many experts and players. So to explain the success of machine learning and deep learning in recent years, one component is probably enabling end-to-end machine learning. So in the past, when we tried to tackle an application, we had to break it down in multiple smaller components. So if we think about speech recognition, for example, audio first has to be transformed into useful representation. And in general, a lot of domain expertise goes into this step. And once we have a suitable or a representation that we think is suitable, then we can start feeding that to, for example, a phoneme recognizer, which would then recognize phonemes and can be done in a data-driven way. And the output of the phoneme recognizer is then sent to, a speech recognizer to produce an output. And so those three steps have to be done somewhat independently, have to be interfaced, and have to work well together. And if one wants to make a change, of the representation, that might have an impact on the phoneme recognizer, and that might have an impact on, in the end, the performance of the final recognizer. So one of the successes of deep learning was to make this process end-to-end, enabling end-to-end learning, where the representation of, for example, in this case, audio, was learned from the data, from a large amount of data, and was learned such that it could produce the best possible output. Now, is this the end of the story? We can do end-to-end learning, but actually, when you think about it, there's still quite a bit of expert domain knowledge that has to be injected. And this is done through expert tuning. Like any machine learning model, any deep learning model has some configuration parameters that need to be set and need to be estimated or tuned. And this is done today by humans. This is done by people that are used to work with certain types of deep learning models, and tuning them might, have a high impact on the performance, and second is usually very painful, very time consuming. So if you want to enable really end-to-end machine learning, even accelerating the use of machine learning to a broader set of problems, we might want to automate this process of tuning too. And having a strategy to do machine-tuned end-to-end learning, essentially using machine learning to tune other machine learning models. And this is what we typically call today AutoML. So as I said, any machine learning model, any deep learning model has quite a large number of, parameters, configurations to set. And it's also true for a broad range of paradigms, going from frequencies to Bayesian techniques. So sometimes people forget that even in Bayesian approaches, one has, for example, to set the parameters or the hyperparameters of the hyperparameters. And those can, in some cases, have an impact on the performance too. So let me look at one simple example, one very textbook example, which is a support vector machine classifier. And let's see what's the impact of the specific hyperparameter settings. So we look here at the validation error for different hyperparameters. So every curve here corresponds to one hyperparameter configuration. And we look at the validation error as a function of the number of training iterations. And the first thing what one can observe is that, the performance, the smallest validation error clusters around two big groups, right? And so Depending on the choice, we end up in one of the groups. And then we see that, well, here, at the bottom here, there are like 2 outliers. And so it's quite probably difficult to find or search over the space of hyperparameters to find those 2 specific outliers that perform much better than the rest, or better than the rest. And so finding them is probably going to be time consuming, and has to be done through some experimentation. Now let's look at the effect of hyperparameters in practice as well. So I'm considering this problem where we have reviews about the product, about the book. And what we would like to do is define whether this review is positive or negative. Like what's the sentiment expressed in the review. So sentiment analysis in those terms is a simple binary classification problem. At least it can be modeled as a simple binary classification problem. And then what we would need to do is pick a binary classifier. We can, for example, take logistic regression, and we need to find a suitable representation. So we could apply standard text feature extractors. So with a binary text classification problem modeled by logistic regression using standard text features, and to train the model, we can use stochastic gradient descent, for example. We can use stochastic gradient descent because we actually have a very large data set, and so this will help us leverage most of the data that we have available for training. So the problem of sentiment analysis was revisited a few years ago, where the authors tried to look not only at how do we optimize the hyperparameters of the training algorithm, like in this case, what type of regularizer to use, L1 or L2, the amount of regularization, when to stop the training, but also to include the configuration parameters of the feature extractors, which was not done very often. Often we have experts some rule of thumb to set to make those decisions, but actually setting them and optimizing and tuning them might have a major impact on the performance. So the authors wanted to look at the end-to-end tuning of this very simple setup by also trying to optimize whether a weighting scheme was necessary, whether one wants to remove stopwords, what was the size of the n-grams to be used in the predictive model. And somewhat surprisingly, once we do this end-to-end tuning, what we observe is that a simple logistic regression with classical text features was competitive with state-of-the-art deep learning techniques at the time. So for example, the model here, this logistic regression model, was performing slightly better than the neural network that was using 1, 2, and 3 grams for representations, and was doing slightly worse than a convolutional neural network using a back-and-forth representation. So in this presentation, I would like to go into more detail into automated hyperparameter and architecture tuning, because those are so find the right configuration of hyperparameter is so critical to the performance, and because this is so painful to do in practice, and so we want to automate that process. And what I'll do in the tutorial is that I first talk about black box global optimization, which is a general framework for tackling this problem. And then I discuss in more detail 2 broad families of techniques. First, I discuss Bayesian optimization. And Bayesian optimization is a family of model-based approaches that are enabling this tuning of hyperparameter architectures. And then I'll move to a more recent set of techniques called multi-fidelity black box optimization, which have been more hungry in terms of resources they consume, but are also very interesting when we have very complex and large problems to optimize, like deep neural networks. So let me start by introducing black box global optimization, which is a general framework for tuning architectures and hyperparameters. So we assume we have a function f, which we wish to optimize, in this case minimize, which is non-convex. So we have multiple local optima, and the goal is to find a good local optimum, possibly the global optimum. And the input dimension of function f is moderate. So we have like a dimension of typically less than 20, which corresponds to the number of hyperparameters we wish to optimize over. So our goal is to solve this minimization problem over some domain X. And the additional complication is that we assume that F is, well, very costly, very expensive to evaluate. It can be noisy, and we don't have an analytical form of F. So that means that we cannot compute the gradients, and this means that we cannot optimize it using standard optimization algorithm. So we are in a situation which is quite complicated, quite difficult, where we want to minimize F, but we cannot compute the gradients, and we can only evaluate it a few number of times to find a global optimum. So when you think about hyperparameter tuning and architecture tuning, well, this can be viewed as a global optimization problem. We have some objective, some metric we want to optimize, for example, the generalization error, and we have some knobs we can turn that impact the performance, impact this objective, the hyperparameters, and other configuration parameters. And we can then measure the quality of the model by applying cross-validation, learning in a cross-validated manner to have like a good estimate of the performance. But every evaluation requires at least to train the model end-to-end based on all the data. And this can be time-consuming. So let us consider this relatively standard problem, which consists in tuning a deep neural net. And here I'm looking at a convolutional neural net. This is the net 5. And if we think about this convolutional neural net, well, F measures the quality of the neural net as a function of its hyperparameters and configuration. And evaluating F can be costly. If you want to train it over large data sets and have a relatively large convolutional neural network, well, training it, so collecting one evaluation can take a couple of hours at least. And the search space, the hyperparameters we want to tune, the architecture we want to tune, well, can be large and diverse. We need to decide about, well, the architecture itself, the number of hidden layers, the activation functions. We need to think about like hyperparameters that impact the model complexity, like the amount of regularization, whether we use dropout or not. And we also need to decide about which optimization are going to use and how to set the learning rates, momentum, batch size. And making the right choice for all those, well, configuration parameters will have a major impact on the performance on the CNN. So when you look at hyperparameter and architecture tuning, well, it is a global optimization problem that requires evaluating many hyperparameter configurations. And this can be very time consuming, especially because this is done through experimentation and relies otherwise on prior experience of the practitioner. So there are a couple of straightforward approaches to tackle the problem, which has been used for years. And the simplest one is to look at a grid search, having a regular grid of hyperparameter configurations and evaluating each one of them. So the problem with that is that the complexity of this regular grid optimization is exponential in dimension, the number of hyperparameters you have to tune. Which means that you will need a very large number of evaluations before hitting the right configuration. So it's very wasteful of resources, but on the other hand, well, it can be parallelized in a relatively trivial way. And you can evaluate every configuration independently, and you will have at least to wait for the most expensive one to complete. A slightly better approach in this family of approaches is random search, having a random grid. And so here, instead of a regular grid, we generate a random set of hyperparameter configurations and evaluate them. And the advantage here is that if there are some dependencies, correlations between the hyperparameters, or some are unimportant, well, we will be more robust, and we will be depending on the effective dimension of, well, the different hyperparameters rather than the real dimension. And the reason is that actually when you generate a random set of, well, configurations, values for those hyperparameters, you will explore more values than in the grid search. And that is an advantage, meaning that you more likely find a good configuration and be less sensitive to the ones that are not really, the hyperparameters that are not really sensitive to the performance, or the performance that's sensitive to the hyperparameters. Now the question is, can we do better? Can we be more data efficient? Those two techniques, they work well, they can be distributed, but as I said, they're very resource hungry. And the number of evaluations that you need number of configurations that you need to evaluate is very large before you find a good solution. So the question is whether we can be more data efficient, and can we learn something from previous evaluations, for example? Or can we try to learn some relationships between the hyperparameters? So to be more data efficient, there is one family of techniques called Bayesian optimization. And the approach is to build a probabilistic model of your objective. So you will take a probabilistic approach for global optimization. And the first step is to build this probabilistic model, which we will then optimize. We optimize this probabilistic model that we learn on the evaluation, so we optimize a surrogate instead of the actual true objective. And we want the model to be probabilistic in the sense that we would like to estimate our confidence about a prediction made by the surrogate. We want to capture uncertainty. And this is a critical component. And it's a critical component because this will enable us to search the grid, or whether random or not, of those points to evaluate by balancing exploration for exploitation. So let me illustrate the exploration exploitation trade-off, right? This very standard problem used in bandits, the bandit syntecture. So we assume we have like 4 slot machines here, and we have some budget that we can spend on them, and want to maximize our return. So picking the slot machine, which is the most interesting to put, well, a large amount of your money. So one way to approach a problem to find the best slot machine is to, well, reserve a small fraction of your money, of your budget, and randomly allocate it to different slot machines. So pulling the arms in a random fashion. And let's assume you have spent some money on the different slot machines, and what you find after some time is, well, the return that you obtain, the expected return for every slot machine. And so what you would like to do now is to say, well, the remainder of my budget, I want to spend it on one of them. Which one? If you just look at the expected return, well, the empirical estimate of that, well, you see that, well, the slot machine number 3 is the most promising. And so you might decide to put all your money, or the remaining of your money, on slot machine number 3, and then hope for the best. But you might also think twice before doing that. And you might also look at, well, the uncertainty, the confidence you have in those expected return that you've computed. And it could well be that the return, the expected return of slot machine 3 is higher than the other ones, but that the confidence is relatively narrow, right? It was relatively stable. And maybe you spend more budget on that one by chance, and so you have a better estimate of your return. But that 2 other ones, for example, 1 and 4, have, well, a return which is slightly worse, but have more uncertainty around this estimate. So if you're less risk averse, you might say, well, it could well be that number 4 is a better candidate than number 3. That if you would have spent more of your initial budget on 4, you would have a better estimate, and that better estimate might be actually higher than number 3. And so this is the basic principle that we will apply to search the space in a more effective way. So Bayesian optimization can be formalized in different ways. And here I will be talking about Gaussian process-based Bayesian optimization. So the problem that we try to tackle is this minimization problem. We minimize f, which is costly to evaluate, over some search space x. And the canonical algorithm for Bayesian black box optimization is the following. So we have a surrogate model M of the objective f, which is cheaper to evaluate. We have a set of evaluated candidates, C, and then we're going to spend some budget. We have some budget available. And so in the first step, we're going to select a new candidate x new to evaluate. based on an exploration-exploitation trade-off that we perform using the model, the surrogate model M. We collect the evaluation y new at this new candidate location. This is a time-consuming step, and then we add this x new to the set of evaluated candidates. With the new evaluation at x new, we can update the surrogate model, and then we can iterate over those different steps until we run out of budget, and we return the best solution that we found. So when we do Bayesian black box optimization of Gaussian processes, we're going to build a surrogate model based on the Gaussian process model. So we learn the probabilistic model of f. We're going to assume f is not observed, so we put the Gaussian process prior over f. So Gaussian process prior is prior over function space. And then we assume some residual noise. So every evaluation y, I at xi, we assume we have some Gaussian noise with some standard deviation sigma. So here we have a function, a target function f of x that we haven't explored. We look at a certain location xi, a candidate configuration to evaluate, and we find yi. After some time, after collecting a bunch of evaluation, well, we can estimate the posterior mean and the posterior standard deviation. So we have the posterior mean here, mu of x, which you can think of as being the surrogate model, and we have some measure of uncertainty, so here sigma x around this posterior mean. And so we're going to evaluate different at different locations where we trade off this a mean function and uncertainty around it. So we repeatedly query f and balance like an exploration-exploitation trade-off. And so essentially there are two components. The first component is the Gaussian process surrogate model, and the second component is an acquisition function that will enable us to do this trade-off between exploration and exploitation. So let me first talk about the Gaussian process surrogate model. So this is typically a standard Gaussian process for regression model. And if you're not familiar with Gaussian processes, there is a very intuitive way of thinking about them. So if you look at a multified Gaussian, so a vector, in this case multiple function evaluations, you can look at the joint Gaussian, multified Gaussian distribution over those function evaluations with some mean and some covariance function k. And the covariance function is going to capture the correlations between those p random variables. When I think about the Gaussian process, well, you don't have p random variables, but you have an infinitely many random variables. So instead of having a mean vector and a covariance matrix, well, you have a mean function and a covariance function. So the nice property of Gaussian processes is that it's a joint density of an infinite set of any infinite set of random variables, but any finite subset is a consistent Gaussian density. The other nice property is that when you assume you have a Gaussian process prior functions here over the target function, and we assume you have a Gaussian noise model, like in the previous slide, well, then you can compute a posterior process in closed form. And it's again a Gaussian process with a mean function of this form, essentially a weighted sum of the evaluations, and some uncertainty around those mean points, where the uncertainty, like the variance, is reduced, as is the prior variance, minus a quantity that depends on how much correlation there is between a point and other evaluations. So more intuitively, what we have is the following. So if we don't see any observations, we can draw functions from the Gaussian process, and here are just three functions drawn from a specific Gaussian process. And once based on some evaluations here, we can compute the posterior Gaussian process. And so we have both like the mean function, so this is, the dotted line is the mean function. And here we have like the corresponding draws from the Gaussian process. And then we have also uncertainty around this mean function. And so we see that near the evaluations, well, the uncertainty reduces, and when you go away from evaluation, you have an increase and more variability. So back to our problem of hyperparameter tuning. So why is a Gaussian process a good, model, is a suitable model for that? So let's assume we have here 4 evaluations. It's a one-dimensional problem here. It's a 4 evaluations. And we would like to know where is there a minimum of f. So we don't observe f, we just have some noisy evaluations of f. So we can draw a first function from this for the posterior Gaussian process, and this function is going through those evaluations, or very near these evaluations, and we find that this here at location 0.4 is the minimum of the function of the draw. We can draw 3 functions and record the minimum, compute a histogram, and so again we have 3 observations near 0.4. And we can continue. This is with 10 draws, and we see that we can gradually build up the histogram of where is the minimum, and continue this process for 100 and 1000 draws. And at the end of the day, we end up with a density of where we've observed the minimum, where, the highest probability here is around a bit before 0.6 and a bit after 0.6. Well, actually the highest is here. So by drawing function from the posterior Gaussian process, we can build a histogram of where is the minimum of this function. Now I mentioned we have the Gaussian process, which is the first ingredient for building the surrogate model. The second one is the acquisition function. So the acquisition function will tell us what is a suitable candidate to evaluate. And the acquisition function is making an exploration-exploitation trade-off. So function A here is a function of, the target objective f that we haven't observed at a certain location x, given, so this is like a sort of a utility function of f at x. Then since we haven't observed, we don't know f, we need to take expectations. So we take the conditional expectation, which is conditioned on the data that we've observed so far. So an acquisition function is a function of every candidate configuration given the current observations that we've seen. So once we have this function, the acquisition function, to decide which is the most promising candidate to evaluate, we're going to maximize it. And to maximize it, we can just apply off-the-shelf solvers. Now, to compute this expectation, we will need the probabilistic surrogate that we've computed. One thing to keep in mind here that it's when we look at the best candidates, what our goal is to find as quickly as possible the optimum of f, or a good optimum of f. So this is a bit different from Bayesian experimental design, where we try typically to cover the space well. Here we're trying to find, we don't try to cover the space, we're trying to find a local optimum. So we might ignore some parts of space that are unpromising, for example. So of course there are a wide range of acquisition functions that we can pick from, and they have different properties. So there are 2 big families. The first family is improvement-based acquisition functions, and I mentioned 3 here. One is probability of improvement, the second is expected improvement, and the third is upper or lower confidence bound. So the probability of improvement is defined in this way, where a of x is the probability that f of x will be lower than the optimum, the minimum value we've observed so far. So it's a quite old acquisition function, and it has the disadvantage of not accounting for the amount of improvement. So in this respect, the expected improvement is looking more explicitly to the amount of improvement that we can see, and it's typically working very well in practice. Now we have an expectation here with respect to f, because we haven't observed f. But when everything is Gaussian, this quantity is tractable analytically and can be optimized. Another more recent criteria is the upper confidence bound, specialized to Gaussian processes. And it has a very natural interpretation. It's essentially a weighted sum of the mean function and the standard deviation. Now it's working very well in practice, except that you have this parameter alpha to set, and there's no good way of really setting these parameters automatically. So it's doing, you can modulate the exploration-exploitation, the trade-off, but there is no good way of setting it like automatically, which then boils on to, again, having the user to have to specify it. A second family of acquisition functions are called entropy-based acquisition functions. And here the goal is to reduce the entropy, essentially looking at information gain of certain candidates in the search space. So we'll not go into the details, but essentially there was first, the entropy search is the one where we look at a reduction of entropy of the probability of the location of the optimum. And somewhat later, another criteria was proposed, which is called predictive entropy, which is an equivalent. It's essentially using identities from information theory. And we have an equivalent criteria, which is more effective to compute. Essentially, in the context of Gaussian processes, one can compute the first entropy term, closed form, and one only has to approximate the second one to, for example, sampling techniques. So the second one is predictive entropy search is more effective to compute. And then recently, it was proposed to look at max value entropy search, where we look at the actual output variables, the optimal. So the mutual information between a new observation and actual minimum of the function, while here we're looking at the mutual information between y and the input configuration. So here this expectation is taken respect to, well, the input space x, which is higher dimension, while here the expectation is taken respect to one dimension, the output space. And so this is has been shown to be, well, it cannot be computed in closed form, but has shown to provide some slight improvements in practice. Just to make things a bit more concrete, how those different criteria perform, acquisition functions. So here we have UCB, upper/low confidence bound, probability of improvement, expected improvement, entropy search, predictive entropy search, and max value entropy search on two examples. And we see that, well, all the entropy search approaches perform similarly, with in some cases, so here we have a slight advantage of max value entropy search, but in other cases, they perform very similarly. So overall, well, probability of improvement is performing worse. You see it here, but both expected improvement and entropy search techniques perform pretty well in practice. Okay, so back to Bayesian optimization now. So we have the two ingredients. We have the surrogate model based on the Gaussian process, and we have a choice of acquisition functions. So let's assume we consider here expected improvement, and let's see how Bayesian optimization works. So in the top figure, we have one evaluation. We have the true objective, which is the dotted line here. We want to find the minimum. So the minimum is near 0.8. And we have the surrogate model. So we have the mean function here, which is like the flat function here going through the observation or near the observation, and some uncertainty around this surrogate, this mean function. And at the bottom, we have like the expected improvement profile. So we see that we have a high expected improvement in regions of space far away from the observation, and well, the expected improvement here is 0 because at the observation we know what's the value. So we're going to maximize expected improvement, and here, well, this is going to be close to the boundary. So the first point which was picked is the one on the boundary, So we're covering the space essentially there initially. We evaluate the function, the target function there, and update the surrogate mul. So with the surrogate mul now is this black curve here, right? And we see that the current best is still this evaluation. We see that the uncertainty here has reduced, and also the value, well, of the information, the expected improvement here is low. So we see that the expected improvement profile has been updated based on the updated surrogate mul. We evaluate the third point. So this was the one picked. It's much higher. This was the one picked. It's much higher. We can update the surrogate mul. We see that, well, expected improvement here is low. And so the next candidate evaluated is this one. And we can iterate the process, update the mul, update the acquisition function profile until, well, we run out of budget. And so we see that after a few evaluations, well, the expected improvement in regions here is relatively low because those evaluations are higher than the evaluation that we found here. And after a couple of more steps, well, we converge to the actual minimum of f, just by relying on the surrogate mul and computing the acquisition function profile and picking the most promising candidates. So to summarize, our goal is to minimize the function f, minimize the error of some machine learning mul or deep learning mul. And the Bayesian optimization algorithm consists in, well, we have our surrogate mul, a Gaussian process mul, which is cheaper to evaluate than, well, f of x. We have the set of evaluated candidates, we have a budget that we can spend, and we select candidate x new based on the acquisition function. So by computing the acquisition function and maximizing it. We then collect the evaluation, which is a time-consuming step, which means that we retrain the mul or the machine learning or the deep learning mul from scratch at this configuration of hyperparameters. We update the set of candidates, and we update the surrogate mul based on the observation. So we compute the Gaussian process procedure. And we iterate this process until we run out of budget, and then return the best configuration. So Gaussian processes is only one specific choice for building a surrogate mul. And essentially any regression mul could be used, provided one also has like estimation of the uncertainty around the surrogate predictions. So I would like to talk about two in particular here, one called SMAC and the other one called TPE. But there are many other choices, and I've added some in the supplementary material of this presentation. So SMAC builds the surrogate mul based on the random forests. So here we see on the left a Gaussian process-based surrogate. So we have the target functions in dotted line, the continuous one, which is like the mean function of the Gaussian process, and then the uncertainty around it, and the red crosses being the observations. And on the right, we have the equivalent random forest surrogate mul. So a random forest is used to mul the observations, and then one can mul the unobserved target function given the data by some Gaussian distribution with some mean and variance. And so what can be observed is when we use SMAC, well, we have to find a way to estimate this mean function and this variance. And one way of doing that is just to use like the empirical mean and the empirical variance at the leaves. And the result is that we have a mul that is doing well where we have lots of observations, but when we move away from the observations, one might, well, underestimate the uncertainty. And in particular, the uncertainty doesn't grow the further away we are from the observations. Also, in some regions, we might be underestimating the uncertainty, although there are no observations. And this can lead, for example, here to some discontinuities in the surrogate mul. Now, those don't seem to be like nice properties. The fact is that even though we see those, well, artifacts, SMAC is a very strong baseline in practice. Another family is based on Parzen window estimators, like based on kernel density estimators. And in this approach, well, we place a kernel density, we estimate the density over the good and the bad configurations. So the first thing is to decide about the threshold, in this case alpha. And so we can then classify the observations are good, bad ones and good ones. So the ones that are below this threshold alpha are the good ones, above are the bad ones. And so based conditioned on the observed evaluation, we can well build a kernel density estimator based on the good ones and a density estimator based on the bad ones. And so we can then compute a ratio and then focus our attention on regions of space that well have promising candidates. So TPE is working very well in practice again. It was proposed before Gaussian process-based ones, at least in recent years. But it has one practical disadvantage. First is that, well, one has to decide about the kernel bandwidth, and choosing that in practice is difficult. And we have to decide about the threshold alpha. And those two parameters are very, are highly correlated. So for some, we can potentially, for a bad alpha, we can compensate by bigger bandwidth and vice versa. But both of those parameters have a strong impact on the performance. Now, this being said, TPEs working can be a strong baseline in practice. And here we see how it performs compared to random search. So we have the performance here on the y-axis and the wall clock time on the x-axis. And we have a comparison of TPE and random search. So we see that early on, well, the two methods do not perform well, but once we have access to enough evaluation, then TPE is focusing its attention on the interesting part of space. And eventually here we see that, well, we can obtain up to 10 times speedups in practice. Bayesian optimization is one model-based approach to black box optimization. A recent trend has been to look at another family, which are more random-based, and which are called multi-fidelity black box optimization. So we've seen that Bayesian optimization is sample efficient because it builds the surrogate model and uses an acquisition function to find promising candidates. But Bayesian optimization is also sequential. There are some non-sequential or parallelized extensions which I haven't had a chance to discuss, but essentially you need to leverage previous observations to make good decisions. And then on the other end of the spectrum, we have random search, which is embarrassingly parallel. Like finding the good configuration, well, can take quite a lot of resources because we explore the space in a random fashion, but you can run all those evaluations in parallel. Now, when you think about training ML and deep learning, well, a training algorithm is inherently iterative. It's costly, but iterative. And one can, for example, monitor the performance as a function of the number of training iterations or number of data points that have been observed so far. So if we think about random approaches, well, a question is maybe, can we use a cheap to evaluate approximation of the target function? Or can we do some form of early stopping? And here on the right, I show, well, a couple of training curves. The validation accuracy as a function number of epochs of the data. And, well, the typical evolution is that, well, it's not monotonous, but it's increasing. The performance is increasing as a function of number of epochs. And we know that we'll see that some of those, well, are at a disadvantage early on. So possibly we could do some early stopping and not fully evaluate some of those candidates. So the approach that was initially explored is this very simple heuristic called successive halving. And successive halving assumes we have some scheduling, or at least some points where we check the performance of different configuration and apply the median rule to stop evaluations that are not promising. So resources are allocated uniformly like across all resources. So we randomly sample configurations, but then we apply early stopping at a certain cadence. So here we have wall clock time. Again, we have validation accuracy and wall clock time as a function of wall clock time, and we have a first check here around a bit before maybe 20 or 25, where we compare the current performance of all the different configuration of hyperparameters. And we apply the median rule, meaning that we look at the top, we stop the bottom 50% and let the bottom top percent continue. We then, like in every group, we let like the resources being constant, so we apply on the remaining curves, we use twice as many resources, and then we do another check. And then we do the same and repeat until we have only a few that are completed until the maximum number of resources. So successive halving has been used for hyperparameter optimization. It can be viewed as a multi-unbounded problem in some sense. And there is one specific choice that needs to be made, is that, well, what's the schedule? What are the resource level? When do we do a check and apply the median rule? And Hyperband is just successive halving at different schedules of comparing the performance of different approaches. So here we have like three rates of stopping configurations. So in the first one, this is the most aggressive one, and here we have a bit less aggressive, and not aggressive, right, where we don't really stop. And for every group of configurations we consume the same amount of resources. So the amount of resources consumed here is the same in the first, what we call the rung, is the same as in the second rung, where we'll have as many configurations I used, but for twice as much time. And so here we have a lot of initial configurations that I explored, in this a bit less, but we only decide a bit later, before killing some of those evaluations. And that has an advantage when, for example, some of the curves could be crossing at some point. We don't really know when is a good time to do the first, truncation or the first stopping of promising candidates, unpromising candidates, sorry. So Hyperband is nothing other than successive halving, where we have different schedules of stopping. It has a very strong anytime performance, and like random search, is very easy to parallelize. But it's using resources in a more effective way than random search, as you don't wait until you finish the training before recording the evaluation. So if we look at Hyperband versus random search, well, we have, first of all, we have a speed up here at the beginning. We have a speed up because we can record the performance at every rung, right? And so because we don't complete a full training before trusting the evaluation, well, we have already like those low fidelity, like early stopped versions of the model. Now, to be fair, one could apply a similar principle to random search. So this speed up could be, it could be reduced if we would record the quality of the models before they're completing the full evaluation. Now, what is probably more interesting is that when we look at a longer time, well, what we see is that applying Hyperband for a random search, well, we can have a potential speed up. Here we have threefold speed up. For the same amount, to reach the same performance, we need 3 times less wall clock time. And look at, and be careful that this is a logarithmic scale, both the performance and wall clock time. So Hyperband is still doing uniform sampling. Like candidates are selected at random, and then they're stopped early or they're not promising. And so the question is whether we can do something better. Can we be, in some sense, explore more promising? Can we guide the search? can we do non-uniform sampling and focus our attention to the parts of space that are much more interesting to focus on. And one approach to do that is called model-based multi-fidelity optimization. And this is combining both, well, the randomized approaches like Hyperband or random search with model-based approaches like Bayesian optimization. So here, if we think about Bayesian optimization, for example, with Gaussian processes, well, one can consider the case where the target function is parameterized by a configuration of hyperparameter x as well as a resource level, the amount of resources that are going to be spent on this particular configuration. And so when R is equal to R max, then we just have the evaluation after a full training path, completion of the training process. And if R is more than R max, well, then we have some form of low fidelity approximation of f of x. So in the context of, well, Bayesian optimization and Gaussian process-based optimization, well, it's very simple, it's very natural to look at that extension. So we now have a function over that takes as inputs hyperparameters and the resource level. And the Gaussian process is defined as over x and the resource level, the hyperparameters and the resource levels, with like an extension of the current function. So this means that we capture autocorrelations within each fidelity. So for some level of resources, we have Gaussian process over function space there. And we capture the cross correlations between fidelities as well. So we can learn from one low fidelity, we can transfer information to higher fidelity regimes as well. So the original paper that was looking at that was looking at BOP, and BOP was based on a TPA-based hyperband, where we had an independent model for each fidelity. So what's the impact in practice? So we have a similar type of experiments here, where we compare uniform versus non-uniform multi-fidelity optimization. We have random search, TPE, which is model-based, which is Bayesian optimization. We have Hyperband, and we have TPE-based Hyperband. And what can be observed is that, well, we have a speed up here, depending on where we, so for example, at this level here, we see that, well, we have the speed up, we see that Bayesian optimization is more sample efficient, so we have a big advantage compared to, well, random search. Hyperband is doing better than random search, but is doing worse than Bayesian optimization. But we see that we have a very large improvement when we combine the model-based approach with randomized approach like Hyperband. So here, at this level here, we obtain like a 50% speed up. And we see that we attain a regret here, which is much lower than any other methods in a smaller amount of time. So we've seen that multi-fidelity and Bayesian optimization can be combined to both make best use of resources, do early stopping, and sample non-uniformly the most promising candidates. Now there is still like a limitation of those multi-fidelity, whether model-based or not, approaches, in the sense that they can only make decisions once all evaluations have reached a certain level of resource consumption, like what is called a run, like the time where decisions are being made. And so one way to improve that and to scale those techniques even further by, for example, leveraging multiple workers is to develop like asynchronous extensions of those. So if you think about Hyperband, well, Hyperband, we could imagine an asynchronous variant of Hyperband, where instead of waiting that all candidates have reached a certain rung, like a consumption of resources, like here, well, might want to do like an early decision on which to continue or to promote. So assume we have like a fixed amount of, well, workers, right? And which are like running some configurations. Well, they reach a rung level. And once they ring, well, they start. And then since they're available, they can start a new configuration, evaluate a new configuration, or if we have enough candidates that attain the rank, we can decide whether to continue promote a variant. Right? And so the way you can implement asynchronous hyperband is to promote when there's a configuration in the top eta% of the configuration that reached a certain rank level. A slightly modified variant, which is actually implemented in Raytune, is to continue as long as a configuration is in top 1 eta of the configuration, the configurations that reached the rank so far. So in this case, you're slightly suboptimal. Well, in both cases suboptimal, but in the second case, you're even further suboptimal. But in practice, there's no big difference between those two variants. And the stopping variant reaches like further like runs of higher resources earlier on than the promotion-based variants. This asynchronous setup can also be leveraged in the case of model-based multi-fidelity optimization. So one doesn't need to wait that all configurations have reached a certain rung before making a decision. And this is especially important when some of those configurations are very time-consuming. Like you can at least use resources to further explore the space while you wait for those expensive configurations that might not be the best ones anyway. And so here we have a comparison between synchronous BOP based on Gaussian processes and asynchronous BOP based on Gaussian process again. Right, this is, in both cases, we have a model-based multi-fidelity optimization based on Gaussian processes, but here we have the synchronous variant and here we have the asynchronous variant. And so what we see here is that, well, we have like the different colors corresponds to when a certain task or configuration was started, and the size of the circles corresponds to the performance. So the smaller the circle, the better the error. So the smaller the error, so the better the performance. And what can be seen here is that by forcing a synchronization point, well, the resources are not allocated optimally, or at least very few configurations end up to the highest resource level. It's a good one, but very few reach that level. While in the asynchronous case, one can be optimistic and just continue one of the configurations and collect data further down the road, closer to the higher level, which is the one that's of interest. And we see here that by doing that, well, we can better allocate resources and explore more configurations up to the highest level. So here we show, well, how both approaches compare if you compare uniform versus non-uniform multi-fidelity optimization. And what you see is that as a function of the number of workers, so we're able to like increase like the number of evaluations by using several workers, and so we have a comparison between essentially asynchronous hyperband, uniform allocation, so the dotted line, and model-based multi-fidelity, model-based hyperband, which is the continuous line. And we see what we would expect, where when you increase the number of workers, you reduce the wall clock time for finding the same performance, and there's a consistent edge for non-uniform multi-fidelity optimization, model-based multi-fidelity compared to hyperband-based. So this is an example where we are tuning the architecture of a ResNet. And so we can further look at other examples where we looked at the tuning of architectures on NASbench 201. And NASbench 201 is a tabular benchmark for neural architecture search, which records essentially we have a lookup table of function evaluations, which makes it much easier or faster to train and reproduce results. And the benchmark contains, well, over 15,000 architectures on 3 different image classification datasets. And we refer to the original paper for the details. And so on this NASbench 201 example, we end up by comparing all the synchronous and asynchronous approaches, both model-based and non-model-based. And so here we have like the three image classification problems. And the first observation is that, well, the synchronous approach are doing worse than asynchronous approaches, which is not surprising. In both cases, they are here on top. And among the asynchronous approaches, we see that, well, the model-based approach is able to improve quite substantially compared to the non-model-based approach, at least in these two first examples. Compared to here, the advantage is less. In all those cases, we've worked on, we've run those experiments on 8 workers, and this is just like a sample of the results that we obtained. So the bottom line is that, well, model-based approaches help you to be more data efficient or focus your attention on important parts of space, and then asynchronous approaches help you scale the process further. And in the same amount of wall clock time, you can explore a much larger number of configurations, which means that you can typically find a better set of good hyperparameter configurations or architectures. So if you're interested in reading more about those topics, well, of course, there is the list of references at the end of the presentation. I would also highly recommend the tutorial by Frank Hutter and Joaquin Wenschoren that was at NeurIPS, well, 2 years ago. There's also like a nice review paper on Bayesian optimization, on taking the human out of the loop, as well as like a presentation tutorial by Peter Frazier on Bayesian optimization too. So what's next? I hope I gave you an introduction of the basic techniques for hyperparameter and architecture tuning. We covered, well, Bayesian optimization, model-based approaches, as well as multi-fidelity approaches and combination of the two, and looked at extensions in the asynchronous case. So next we have like an overview of AutoGluon toolkit in one of the next tutorials, a presentation on neural architecture search, and then a couple of hands-on tutorials. One on multi-fidelity, one on proxyless NAS, and one on fast auto-augment. I hope you will enjoy your time and enjoy the tutorials. Thank you for listening.